Okay, section 13.2 is our next two conics. It's ellipses and hyperbolas. So we have, I have this as one objective, but it's really two objectives. So we're going to define and graph ellipses and then hyperbolas. So let's talk about an ellipse. So an ellipse with center or with a center at 0, 0, the origin, has the equation x squared over a squared plus y squared over b squared equals 1. And it has x-intercepts a comma 0 and negative a comma 0. It has y-intercepts at b comma 0 and negative b comma 0. And if a is greater than b, then the x-axis is the major axis of the ellipse. If b is greater than a, then the y-axis is the major axis. And the non-major axis is called the minor axis. So this is what makes an ellipse. Now, one thing to note is when a equals b, this is a circle. So you'll never have an ellipse where a squared equals b squared. You'll never have an ellipse where a equals b because those are circles. So there's 4 big components to every ellipse, specifically centered at the origin at 0, 0. You have your intercepts, the x-intercepts, the y-intercepts, and then you have your axes, the major axis and the minor axis. And it comes down to just looking at the numbers. So when a is the bigger number, a becomes your major axis, the x becomes your major axis because it's under the x. When b is bigger, then the y becomes the major axis. And then if you're not the major axis, you're the minor axis. Not too much different terminology. So let's look at graphing one ellipse. And I'm going to switch papers because not enough space. Right, too big. So let's graph x squared over 9 plus y squared over 16 equals 1. So first things first, our center is 0, 0. Our major axis is the y-axis. That means the minor axis is the x-axis. And so now we look at our intercepts along the y. If b squared is 16, that means it's 0, 4 and 0, -4. And along the x, a squared is 9, so it's 3, 0 and -3, 0. The nice thing about ellipses is as long as you identify your intercepts correctly, you don't actually need to identify your major and minor axis. You just need to double check after you graph that this works out. So what we mean by major axis is this is the longer axis, right? Ellipses are like flattened circles. And so when you flatten that circle and you squish it down, you're going to extend one of the axes. Your major axis is the axis that was extended. Your minor axis is the one that's getting squished to form the ellipse. So when we go to graph this, we need some axes. So I need to get out to 3, so we'll go 1, 2, 3. And we'll go by 2s, 4, 6, 1, 2, 3, 4, -2, -4, -6, -8, 1, 2, 3, -2, -4, -6, 1, 2, 3, and this is 2, 4, 6. So we're going to plot our intercepts. 0, 4, 0, -4, 3, 0, -3, 0, and then we draw an ellipse. And this one's almost circular because the x-axis, the major axis and minor axis are only off by 1. So you can think of the minor axis is the length of this, which is only 1, 2, 3, 4. 1, 2, 3. Its length is 3 and then 6, so 3 to 3, it's 6, and the length here of the major axis is length 8, 4 down to 0, 0 down to -4. Right, so, and then we plot these. Its center 0, 0. So 3, 0, 0, 4, 0, -4, and 4, and -3, 0. That's our ellipse. And for these types of ellipses where the center is at 0, 0, just like with the circle, it's real easy. As long as you're identifying your intercepts correctly, you can't go wrong. So let's take a look at what happens when we're not centered at the origin, because those are the more interesting ellipses. So this is the standard form for an ellipse. So the standard form is x minus h squared over a squared plus y minus k squared over b squared equals 1. So nothing changes except the center is at h comma k, and then our intercepts are, instead of 0, 4, 0, -4, or 0b, 0, -b, you take your hk and you do h plus a, comma k. You do h minus a, comma k. You do h, comma k minus or k plus b, and h, comma k minus b. And again, your major axis is the axis whose denominator is larger, so if b is bigger than the y-axis, the vertical axis is still the major axis. And you just take your center and you add and subtract the A from the X's and the B from the Y's. And those give you your 4 points. So let's take a look at an example of this. So let's start with graphing x plus 3 quantity squared over 25 plus y minus 2 quantity squared over 16 equals 1. So the first thing we want to do is identify our center. The center, -3, 2. So just like with circles and parabolas, standard form has a minus inside, minus, minus. So if it's plus, that means it's negative here on the center. Our A value is 5. Our B value is 4. So our major axis is going to be the x-axis. And then our intercepts, -3 plus 5, 2, which is 2, 2. -3 minus 5, 2, which is -8, 2. Then we have -3, 2 minus 4, which is -3, -2. And then -3, 2 plus 4 is -3, 6. So these are our 4 intercepts. Now I'm using the term intercepts, but they are no longer intercepts. So if you want, you can put this in quotes. But these become what we call the vertices of an ellipse. So now we go to graph. These are the edges. So you can kind of look at this as what you need to get to on the x's. I need to go all the way to -8. On the y's, I need to go all the way down to -2 and up to 6. So I'm going to scale 1, 2, 3, 4, 5, 6, 7, 8. Make that a little bit longer. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4, 5. So this is 1, 2, 3, 4. We're going by ones. -1, -2, -3, -4, -5, -1, -2, -3, -4, -5, -6, 7, -8, 2, 3, 4, 5, 6. So we're going to plot these 4 points and our center. So -3, 2. Right there is our center. Let's do this in a different color. -3, 2. And then our intercepts, our vertices, we have 2, 2, 2, 2. We have -8, 2. We have -3, 6, straight up. And then we have -3, -2 down here. So you'll notice you'll have made a nice cross here. And that's what we should do. So now we connect these points. And label them 2, 2, -3, 6, -3, -2, -8, 2. And that's our ellipse. So, not too bad. All you have to do is make sure you identify your center correctly and your a and b values. A always gets added to the x and subtracted from the x. B always gets added to the y and subtracted to the y. And you can remember that because the b comes from the y term and the a comes from the x term. But that's how we graph ellipses, general ellipses. So our next conic is the hyperbola. So for a hyperbola centered at the origin, 0, 0, we have two types, just like we had two types of ellipses. You can think of them as the horizontal ellipse, where our major axis is the x, and the vertical ellipse, where our major axis is the y. We have two types of hyperbolas as well, horizontal and vertical hyperbolas. Now, hyperbolas are the most complicated of the four conic sections that we're studying. And so we're going to break them down one at a time. So the first type looks like this: x squared over a squared minus y squared over b squared equals 1. So notice this is very close to an ellipse, except it's a minus here. And so this tells us that the x term is the positive term. So we have intercepts, x-intercepts, at a comma 0, negative a comma 0. And we have the y term is negative, so there are no y-intercepts. So that's how you tell the two apart. And you'll see in the next version where we'll have the x term being positive and the y term being negative. The next piece of information that we know from this is that a squared greater than b squared, and we have asymptotes through two sets of points. So there are two asymptotes. The first asymptote goes through negative a comma negative b and a comma b. And the second goes through negative a comma b and a comma negative b. And in general, the graph of this hyperbola if this is a and negative a, and this is b and negative b, we have our asymptotes that go through these 2 points, these 2 pairs of points. We have x-intercepts here and here. And our hyperbola looks like this, never crossing these asymptotes. So this is what we call I call it the horizontal hyperbola because it's opening along the horizontal. And that's generally what the graph is going to look like. The second type of hyperbola is negative x squared over a squared plus y squared over b squared equals 1. So notice the difference. The negative has switched positions. So in this, the x term is the negative, so there's no x-intercepts. The y term is positive, so the y-ints, the y-intercepts, are at 0, comma b and 0, comma negative b. So we said that a squared should be bigger than b squared. We should make a note that this is not always. That's just tradition. And here b squared can be bigger than a squared, but again, this is not always. And our first example will be one of these not always cases. It doesn't change how we look at our hyperbolas, it just changes their shape a little bit. And our asymptotes luckily go through the same combination, so negative a, negative b, and ab, and negative a, comma b, and a, comma negative b. So we don't have to learn two new asymptotes, which is nice. They go through the same set of points. And our general shape of this hyperbola that I call the vertical hyperbola looks something like this. So again, if this is a and negative a, and this is b and negative b, our center at 0, 0, we have intercepts, negative b and b, and then our asymptotes go through AB and negative a, negative b. That at a, negative b and negative AB, like that. And our hyperbola looks like this, not crossing our asymptotes. Well, I did a real bad job on that one. All right, again, this is just a quick sketch, but that's the general shape of our hyperbolas. So there's actually a really nice way to graph hyperbolas that make them both easy and look good once you've graphed them. So let's take a look at an example or two of hyperbolas. So let's graph x squared over 16 minus y squared over 25 equals 1. So our center is 0, 0. Our a value is 4, our b value is 5, and we have no y-ints, no y-intercepts because the y term is negative, which means our x-intercepts are 4, 0, negative 4, 0, and our asymptotes go through the pairs 4, 5 and negative 4, negative 5, and 4, negative 5 and negative 4, positive 5. So if we go to graph this, let's talk about how we can make this a little bit easier on ourselves, both graphing and make it look good. So we need some axes. I'm going to go 1, 2, 3, 4, 5, 6. Go by 2, 4, 6. So scaling by ones. 1, 2, 3, 4, 5, 6. 2, 4, 6 negatives. 1, 2, 3, 4, 5. And the positives. And 1, 2, 3, 4, 5. In the negatives. So the way that we make this easy, we call this the box technique. So you look at what your intercepts are, you've identified them, so we can plot those right now, negative 4, 0, and 4, 0. And then we make a box up to where our b value is, and over up to our b value from the other intercept, and then down to the negative b value across. So we do this because now our asymptotes go through the corners here. So the first asymptote goes through that corner. The second asymptote goes through these corners. And if you do this, you'll have a nice shaped hyperbola, because now our hyperbola just has to match the asymptotes. And you have the box kind of as a guide. This is 4, 0. This is negative 4, 0. And we've graphed our hyperbola. So the box method is there to make your asymptotes easy to remember. So if you ever forget how to find your asymptotes, you should always know how to identify your A and B. Just make the box that has corners at all the A and B values. So positive A, positive B, positive A, negative B, negative A, positive B, negative A, negative B. So if you make that box, you can even do that first, because you're always going to make the box. So let's look at another example, and we'll do the box first on this next example. So let's graph 4y squared minus 9x squared equals 36. So the first thing we have to do, since this is not in proper form, is divide everything by 36. So 4 over 36 becomes y squared over 9 minus x squared over 4 equals 1. So now we have our hyperbola. Now be careful. Notice from the last example, the x and the y have traded positions. That's okay when you're dealing with any conic. You need to keep track of where the sign is. So the x term is negative, which means no x-intercepts. Our y-intercepts, 0, 3, 0, -3, because a is still the x term is 2, and b is still the y term is 3. So remember, a and b are linked to x and y respectively. This never becomes your a, even if the y is first. The a is always the square root of the number under x. B is always the square root of the number under y. So those are our intercepts. Now let's do this as if we forgot about the asymptotes. We forgot how to find them. So you're working on your test or your quiz, and you go, oh crap, I don't know where my asymptotes are supposed to go. If you just memorize how to do the box technique, that we just outlined. So give yourself some axes. We need 2 and 3, so 1, 2, 3, 4. Go by 2s. 1, 2, 3, 4, 5. -2. Oh, I'm sorry. That's -1. -2, -3, -4, -5, 1, and 3. We'll add them in. 1, 2, 3, 4. -1, -2, -3, -4. And then 1, 2, 3, 4, 5. 4, 5. So we've forgotten about the asymptotes. We can't remember, but we're not going to get stressed because we're going to just use the box technique. So A is always the X, is 2, B is the Y. So I'm going to come up like this, up to Y, up to the B, over to the -A, down to the -B, and then back over to the A. And I make my box. The X term, if you remember what that is, so it's negative, so our y-intercept, 0, 3, 0, -3. Our asymptotes always go through the corners of these and through the center. And then we have our intercepts. We just sketch our hyperbola using the box and the asymptotes as a guide. This is 0, -3. This is 0, 3. And we've graphed our hyperbola. So if you do anything, I would recommend you just memorize how to identify the correct A and B, A coming from the X, B coming from the Y. Sketch your little box as your guiding line to get your asymptotes, and you'll always have a good-looking hyperbola. And that's all there is to it for hyperbolas. So that's the end of 13.2.